definition of the orthogonal projection onto a subspace W of V should have the following properties. One, the projection alright, so the projection of X onto W should be in W. Okay, so the first one. The second is that the difference between the original vector X and its projection, its orthogonal projection onto W should be orthogonal to every element in W. Okay? So a picture so this is V, this is W, okay, and suppose this is the origin of your vector, okay. And suppose we have this X here, and the projection onto W should be something, a vector here, so that the difference, so this is the projection, X, and the difference should be orthogonal to any Y, okay, in W should be orthogonal. So that orthogonal means that we have a right angle here, right angle there. Okay. So the orthogonal projection, this is maybe I write here. Okay. So the orthogonal projection, the notation is here, PROJ sub W X. Okay. The orthogonal projection onto a subspace W of V of X, I'm sorry. The orthogonal projection of X onto a, sorry. You have to put of X. So that this orthogonal projection should be in W, of course. So the yellow vector should be in W. And the difference, the red should be orthogonal to all the vectors in W. Okay. Okay. So to have a proper definition, okay, now we let W be an m-dimensional subspace of V. Right? So suppose when we let B U1, U2 up to UN be an orthonormal basis for W. Okay? Right. Now, by the first requirement, alright, by the first requirement, i.e., the projection, the orthogonal projection should be in W. So the orthogonal projection of X onto W should be in W. We have that the projection X equal to alpha 1 U1 plus alpha 2 U2 plus plus alpha M UM. Okay, so we should have for this one, right? By the first requirement. Now by the second requirement, i.e., X minus the summation I from 1 to n alpha I Ui and Uj must be equal to 0. Okay? For all j from 1 to n. Assume we have, okay, because we are asking for the difference should be orthogonal to every element in W. But this is equivalent to saying that the difference is orthogonal to every vector in the basis. Because if this is true, if the difference is orthogonal to every element in the basis, then it should orthogonal to every element in W. Okay. Because the linear combination, because in W, a vector in W is just a linear combination of a vector in the basis. Right, so that's equivalent. So we have that. Okay, this is for all j from 1 to m. And then this one, okay, by the linearity of inner product for the first argument, so this is X Uj minus summation I from 1 to m alpha I Ui Uj equal to 0. Okay, for all j from 1 to n. Oh, and furthermore, I think, okay, here, right, I write it here. Now, what is that? This is delta ij, because that the UIs are also normal. Okay. So this is delta ij. All right. So this says that xuj is equal to summation of I delta ij. Okay. But so this is equal to alpha j. Okay, for all. Alright, so we find that alpha j, the coefficient, is just the inner product of the vector x and the uj. So we have, so the projection, so this one, it becomes to so the projection is uniquely determined by okay, all right. So now the projection, we have the formula. Okay, so with such a definition, means that by using two requirements, that is very reasonable, right? Reasonable requirements here. We find that the orthogonal projection of a vector x onto a subspace W, right, can be obtained, expressed in this way. Okay, and it's definite, right? This is the unique one. And with the help of an orthonormal basis B here, right, for the W. Any questions? Remark, you see, from here, from this definition, so with projection equal to this is necessary condition, but we have to say this is also sufficient. Why? With this one, we have one, the projection is in W, of course, right? Because that is a linear combination of UIs. And UIs are vectors in a basis B for W. So of course, and second, we check Uj. Okay, so we check. And we check that, so this is the x minus summation okay, right? And so that would be okay, and this is delta ij. Minus, and when I equal to j, this is 1, so we have, and this is 0. So all so that x and projection this is 0 for all 1. So we showed again that with this definition, with this expression, this expression satisfies 1 and 2, the first two, these two requirements again. Okay? So they are equivalent. So to say that the orthogonal projection satisfying these two properties is equivalent to saying that this projection of x onto W is equal to this summation, this linear combination of UI. And the coefficient is just the inner product of the x and the UI. And it is very important that the UIs form an orthogonal basis for the W. Any questions? Okay. Okay, so later on, you will have two definitions of orthogonal projection of a vector onto a subspace. One is that we define this projection by this modular directly. The second is using these two properties, saying that the orthogonal projection of x onto a subspace W should satisfy these two requirements, and they are equivalent, okay? As I just proved for you. Is that okay? Any questions? Okay, so if there's no questions, then right. So now we will give a theorem 7.1c. Let W be a subspace of an inner product with okay? Oh, sorry, we are finite dimensional. Subspace, okay, of an inner product space. Okay. Right. So it's very important that W is a finite dimensional space. So that then for each vector in V, the projection of x onto W has a polar property that the difference, the distance from x to a position, so the distance from x to this projection would be the minimum of Oy in W. Okay. We have, first of all, the projection like that, and the orthogonal projection of x onto W is the unique vector in W having this property, having this minimum property. Okay. So this will be another, and we will see this is another definition for that. Right, so we do for proof. Let y is in W. Alright, so now x minus y, to look at the square. Then this square is that x minus projection minus y minus projection. Okay? But the difference of x and the projection is orthogonal to every element in W. And remember, projection is in W, so this different, the linear combination, this one, also in W. So that they are orthogonal. Alright, so this vector is orthogonal to this vector. Okay. I think I have to put plus projection minus 1. Sorry. Yeah, add 1 and minus 1 and add 1. So I have to. And so they are orthogonal and by the Pythagorean, because orthogonality implies the Pythagorean equality. So that this is come to x minus projection square plus things. This one orthogonal to that they are orthogonal by the second requirement. Okay, and so the lower bound is okay. This is the lower bound. Why? Because the square, this one is always non-negative. Okay? And the equality, so we have lower bound. And equality holds if and only if that the projection y is equal to the projection. Okay. Why? Because if y is not equal to the projection, this is non-zero. Okay? And if we have non-zero vector, the norm is non-zero. Okay? So we cannot have the equality. So equality holds if only y is equal. So this proves that so this shows that this one is the minimum. Okay? Or so that projection is the unique vector in W such that this one is the minimum. Okay? But we have to conclude. Any questions? Any questions? All right. So if there's no question now, we let X be a subset of an inner product space V over R of C. Okay. The orthogonal complement X per of X is defined as the S curve is defined to be all vector in the interval class space such that the vectors is orthogonal to every vector in S. That is called orthogonal complement. So every vector in the orthogonal complement should be orthogonal to every vector in X. Okay, now we prove a lemma 7.8, which is just theorem 7.1.14 in the textbook. If S so let P be subset of an inner product space. Okay, so suppose we have two subsets, X and T. If S is smaller than T, if S is smaller than T, then the orthogonal complement of T will be contained in the orthogonal complement of S. Okay, so you have to reverse the order. So smaller subset has bigger orthogonal complement. Proof. Okay. Right. Suppose X is a vector in the orthogonal complement of T. So that means that if and only if X is orthogonal to V for all V in T. Right. So X is orthogonal to every vector in T. So that implies that X is orthogonal to every vector in S because X is smaller. And so this is if and only if the X is in the curve. So we say that X in T curve implies X in X curve. So that says that T curve is contained in S curve. Okay. You may simplify that. Okay, just saying that. Okay. Alright, so now we prove theorem 7.1.6. Let X be a subset of an inner product space. V. Then S curve is equal to the curve of span of S. so that the orthogonal complement of the subset is the same as the orthogonal complement of the subspace spanned by the subsets. So proof, because that X is contained in the span of X, so this implies that the span of the curve of the span of X is contained in the curve of this by the previous lemma. Okay, so this. Okay, so to establish the equality of two sets, we have to prove one contains in another, right, each other. Okay, so this one. Now, for X in the orthogonal complement of X, this implies that X is orthogonal to V for all V in X. So that this means that X, V, inner product is 0 for all V in X. So this implies that alpha 1 bar X V1 plus alpha 2 bar X V2 plus alpha n bar X Vn is 0, right? For all V1, V2 up to Vn in S. For all alpha 1, alpha 2 in alpha n, and for all scalars, and scalars alpha 1. Right? And by conjugate linearity for the second argument, so we have alpha 1, V1 plus alpha 2 equal to 0. Okay? For all V1, V2, capital Vn in S, and scalars alpha 1, alpha 2, up to alpha n. So this implies that X is 0 for all U in the span of X. Okay. Because every element in the span of X can be expressed as a linear combination of vectors in X. So this is true. And so this implies that X is in the span, is in the orthogonal complement of the span. Alright, so we start from here and end up with there. So this implies that contain. Right, and the conclusion is that this is equal to so the theorem is important. For example, if we are considering a subspace and we want to know the orthogonal complement of a subspace. We can select a basis X, right? A basis of the vector space. So X is the basis. And so the orthogonal complement of this vector space is equal to the orthogonal complement of its basis. Okay? Basis. Alright, so we have theorem 7.1.7. So let X be a subset of an inner product space. Really? Then X curve is a subspace of V. Okay? The proof. Since 0 is orthogonal to every element, so Z should be in the, so 0 vector should be in the orthogonal complement. Because 0, as we noticed that 0 vector will orthogonal to every element in the vector space V. So that this is true. Now let X, alright, so it's non-empty, okay? Let X and Y be in the S curve, i.e. X means that X is orthogonal to V and Y is orthogonal to V for all V in the subset X. That's X plus Y, and V, that's for all V in X plus Y, V equal to X V plus Y V. So this is 0 to 0 and then equal to 0. So this implies that X plus Y is in the orthogonal complement of X. And alpha X, V, and so this is alpha X V, alpha 0, so it's 0. So this is implies that. Okay. So we show that the addition of two vectors in S perp is also in S perp, and the scalar multiplication of a vector in the S perp is also in S perp. Okay. So that we conclude that S perp is a vector space. a vector subspace of V. All right. So now we prove a bigger theorem on point 13. Right, let B be an n-dimensional inner product space. Okay, so V is n-dimensional. And let W be a subspace of V. Then the dimension of W plus the dimension of the perp of W is equal to the dimension of V, which is equal to n. Okay, so we give a proof here. So let M to be the dimension of W. Right? And of course it's less than or equal to the dimension of V. As we know before, and we let B equal to U1 U2 up to Un be a basis for W. Right? So we have a basis for W. Then B can be extended to a basis for C U1, U2 up to UM, and UM plus 1, so that UN for V. Okay. So we know that we can do that, so by extension. Then every vector in the inner product space V has a unique representation. Okay, as a linear combination of UIs, I from 1 up to N, i.e., we can write down this unique representation X alpha 1 U1 plus plus alpha M UM plus alpha M plus 1 UM plus 1 plus alpha M UM. Okay, so every vector in V can be represented here. Now, X is in the thermal complement of W, if and only if X and the Uj is equal to 0, for all j from 1 to n. Because the u1, u2 up to um form a basis for w, so that x is in the orthogonal complement of the if only if this is true. Alright, so this is saying that summation of I from 1 to n of I, ui, uj equal to 0 for all 1 up to j up to m. So this is saying that n alpha I and ui, uj equal to 0 for all 1. Okay? So we have to solve the coefficient of our i's, satisfy m linear equations. Okay, so we can write down here u1, 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 u2, u1, un, u1, up to u1, un, u2, un, un. Okay. All right. So this system linear equation can be written by a metric equation. Yeah. And this matrix has m rows, so it's m times n matrix. This is n times 1, and this is m times 1. Okay, so we have a homogeneous. We have a homogeneous. All right, so we have a homogeneous linear system. Okay. All right, and so we call this matrix as A matrix, and this as the the coefficient, so it's like A here, okay. And of course this is 0, your vector, so that this is A vector, which is alpha 1, alpha 2, up to alpha n. All right, it's in the kernel of A. So that's the dimension of curve is equal to the dimension of the kernel of A. And so this is the nullity of A. Because every vector in the kernel of A corresponding to a vector in the orthogonal complement of W from here, because of the representation. This is just the coordinate, right? The coordinate. So this is actually the coordinate vector of the x relative to this basis C here. Okay. So that they have one-to-one correspondence. In chapter 5 we studied. And so the dimension, because they are isomorphic to each other, so the dimension of this curve is equal to the dimension of the kernel of A, and this is called the nullity here. Now, we will claim that, so the claim, the set of all rows in A is a linearly independent set. Okay, so we claim that. We have m rows, and we claim that these m rows are linearly independent. Okay? So the rank of the matrix A will be equal to n. Right. So we have to prove that the coefficient matrix A has linearly independent rows. Okay. So now consider an arbitrary linear relation on the set of m rows of A. Okay? The m rows of I use AJI with AJI equal to the U I U J. Okay. Okay. Right. So we consider now C1 bar 1 plus C2 bar 2 plus Cm bar m equal to 0. Okay. And the coefficient, a linear relation, for our purpose, I just put the complex candidate. That's fine, because an arbitrary linear relation can be written in this way. And R1, R2, Rm are m rows of the coefficient matrix A. So this implies that C1 bar, A1I plus C2 bar, A2I plus plus Cm bar, AMI is equal to 0 for all I from 1 to n. Okay? Because this is 0, so every component should be 0. Okay. And so this means that C1 bar and AJI is equal to UI, UJ in the product. So we have UI and U1 plus C2 bar, UI, U2 plus plus Cm bar, UI, UM equal to 0 for all I from 1 to n. Okay? And now, by conjugate linearity for the second argument, so we will have UI, and we have C1 bar, U1 plus C2. Oh, there is no bar at all. So we have C1, U1 plus C2, U2 plus plus Cm, Um equal to 0. Okay? For all 1 to I and 2. Okay? Alright, so up to now we have done by direction. So there you have only distribution. Okay? So this is true. Now, because this is true for all I from 1 to n, now this implies that we take C1, U1, and the summation here, okay, can be written by j from 1 to n, Cj, Uj. Right. So I take I equal to 1. This is 0, but by a multiply with C1 plus C2. I use U2 summation. Right? Now I take I equal to 2, put here and multiply with C2. And up to Cm, Um, summation, j from 1 to m, Cj, Uj. Okay, this is also equal to 0. Right, so this implies cannot go back, okay? We cannot go back because we use this condition that this is true for I from 1 to n. So for each I from 1, 2, up to n, the interval, this is 0. This is 0. So when we multiply C1, C2, then this is also 0 too. Okay? So that is the idea. Right? Because everyone is 0 from here already. So C1 times 0 plus C2 times 0 plus Cm times 0 is 0. Right? Any confusion? If there is no confusion, then with linearity for the first argument. So now this implies that C1 U1 plus C2 U2 plus plus Cm Um summation j from 1 to m, Cj Uj equal to 0. So this is implies I from 1 to m, Ci, Ui, j from 1 to m, Cj Uj equals 0. But these two vectors are the same. So by non-negativity of inner product, we have summation I from 1 to n Ci Ui equal to 0 vector. And this implies that because Ui's are linear independent, so C1 equal C2 equal to Cm equal to 0. Okay? So let's see, they are all equal to 0. So that implies that C1 bar equal to C2 bar equal to Cm bar is 0. So we start with a linear relation on the set of m rows of A. We find that the coefficient must be 0. So that R1, R2, up to Rm is a linearly independent set. Right? So this is the linear independent set. So the m rows are linearly independent. So that the rank of A is equal to m. And this implies that the nullity of A is equal to m minus m. By the rank nullity theorem. Okay? In chapter 5. So in chapter 5, we proved the rank nullity theorem. Okay. So now this is n minus m. So now dimension of W plus dimension of the curve. This is equal to m plus m minus m. So this is n, so this is dimension of width n of 2. Okay, so let's take a short break for 5 minutes in the circle complement. Right? So this is the definition. Because every element in W will orthogonal to every element in the orthogonal complement. And so that X is in curve. Alright? So we have the W contained in here. Any questions? Okay, so now by the previous theorem, so or from the previous theorem, the dimension of W plus the dimension of curve is equal to n. And again, if we apply to this subspace, we will show that this is a subspace of the W. plus dimension of is also equal to n. Yeah. And then we do so we compare, then we do the subtraction, so we find the dimension of W is equal to the dimension of curve. So they have the same dimension. Alright? Now, so if W is a proper subspace of this double curve, then we cannot have this one. So this implies that W is equal to, there is no other choice. We must have this identity. Okay. Because they have the same dimension, and the W is a subspace of this double curve of W. Okay, so we have this one. Now, consider another lemma. So let W be a subspace of an inner product space V. Then the intersection of W and the W curve is the zero vector moment. I think the proof is quite easy. Let V be in the intersection. Alright, then we have V and the V is equal to 0. Why? The first V, can we think about that, is in what? In W. And the second V is considered an element in W curve. And as we see that any vector in W is assigned to any vector in the W curve. Okay, so that this inner product should be 0. And by non-negativity property, this is equal to 0 vector. Okay? No other choices. Okay, so now we prove the last theorem for section 7.1. Let W be a subspace of an n-dimensional inner product space. V. For each vector in V, there exists unique U in W and V in the curve of W such that X is equal to U plus V. So we have a unique decomposition, to decompose any vector X in V into two parts. One is a vector in W, the other is a vector in the orthogonal complement of W. So this is called the orthogonal decomposition. Okay. Right? So we have orthogonal decomposition. And this decomposition is unique. So let's prove. the uniqueness first. Assume that there exists U prime in W, and V prime in W, such that X is equal to U plus V, and X is equal to U prime plus V prime. Okay? Suppose that. So now U plus V equal to U prime plus V prime. So this implies U minus U prime equal to V prime minus V. Okay? And now U minus U prime will be in W, and V minus V prime will be in the term. Okay, so there must be in the intersection of these two subspaces. So that this implies that U minus U prime equal to V prime minus V equal to 0 vector by lemma the previous 7.1.2. So this implies that U equal to U prime and V equal to V prime. Right? So we have uniqueness. Okay. So if we have such a decomposition, then this decomposition must be unique. The second part is the existence. Alright, so we let U to be the projection of, right? So this U just the projection of the vector X onto the subspace W. Alright? Alright, so we let, and we define to be the X minus projection. Okay? Now, U should be in W by the first requirement. Right? As a orthogonal projection of an orthogonal projection. Right? So this is from the first requirement, because the projection of X onto a subset W must be W. And also by the second requirement, of the orthogonal complement orthogonal projection, sorry. Projection the difference vector must be orthogonal to, right? So this implies that the V as defined by is in the perp in the orthogonal complement by definition, right? So that's fine. Alright, so that as X becomes to U plus V. And we have the composition already. With U equal to a projection in W and V equal to X times projection. And we have that. So this is exactly what we have from the orthogonal projection. This property, orthogonal decomposition, is a special case of direct sum decomposition. So let me see. Let U and W be two subspaces of vector space. Not necessarily inner product, just a vector space. And U and V be two subspaces. V is called the direct sum of sub and of U and W, denoted as V equal to U direct sum with W, right? If two things, one, if V equal to W, U plus W, what is that? This is U plus W for all U to U and W. So first of all, V is the sum of U and W. The sum of two subspaces is just the sum of elements U from U, capital U, and W from capital W, right? And the UW is the trivial. And the intersection of U and W is just the zero vector. Okay? So direct sum is that V is the sum of two subspaces U and W, and also U and W satisfy this special property that their intersection is trivial. Just consist of zero vectors. So now we have it can be shown that so that the theorem 7.1.11 is equivalent to saying that for a finite dimensional inner product space, V is the direct sum of W and the curve for any just saying that because we show that V is the direct sum. It's the sum of V and V perp. And we have shown in the previous lemma that W and the W perp, the intersection of them is just the trivial space, means that it consists of only the zero vector. So we have the previous theorem saying that V is the direct sum of W and the W perp for any subspace of W. Okay. Any questions? Now we move on to the second section of chapter 7. About orthogonality. And the purpose of this section is that in this section we will show that we can construct orthonormal basis right? We can construct orthonormal basis for any n-dimensional inner product space. Okay. And we will start with a basis. So in general, let x u1, u2 up to un be a linearly independent set. In an inner product space. Right? So we just take an arbitrary linearly independent set. And this linear independent set has m elements, m vectors. We want to construct. So we want to construct an orthonormal set called Q. Q1, Q2, up to n, such that they span the same vector subspaces. The same vector subspace. Okay. So, given the linearly independent sets, this linear independence becomes to a basis for its spanning subspace W here. And then we can construct, from here, we can construct an orthonormal set. Okay? So that this orthonormal set becomes to an orthonormal basis for the W. Okay? Right. So now we will demonstrate the procedure. Alright, so this is called the Graham Schmidt procedure. Right? So I will demonstrate the Graham Schmidt procedure. So it's an algorithm, okay? It's an algorithm. We can write a C code or Python code or C++ code to, and the input is just a linearly independent set. Say here, and the end up is a normal set. Okay? First, Q1, the first element. Alright, and Q1 is just U1 divided by its length. So it's simple. It just normalize the U1 only. Okay? So in this case, the span, so that in this case W1 defined to be the span of U1, the set span by U1, and this is of course equal to the span of Q1, because Q1 is just a scalar multiplication of U1. So we have this one. Okay, no problem with that. And Q1 is an also normal basis for W1. Okay? Just only one, so there is, you can say that it's an also normal basis. Now, the second one, Q. The second member in this orthonormal set is obtained in this way. Is that the U2 minus the projection of W1 and the U2. Okay? So we project U2, the second member in the linear independent set, project to W1 and take the difference and then normalize the difference. Okay, so we always need to normalize it. Okay, so the projection. And this is equal to, because from our definition, because we found an orthonormal basis for W1, right? So the projection is just the U2 and Q1. U2 minus U2, U1. Okay. Because this one is just a projection of U2 onto W1. Alright? Now it is clear that now think U2 minus U1, U1 is orthogonal to U1, right? Because of projection, so we have that, so thing. So we have the Q2 is orthogonal to Q1 because you just normalize it. Okay. So now you have Q2 orthogonal to Q1. Okay, because now we have this, because they are orthogonal and normalized. Okay? Also, since from here we know Q2 is equal to projection plus U2 minus projection of 1 U2 times U2. Okay. And this is equal to U2 Q1 plus U2 minus U2 Q1 Q2. So it's a linear combination of Q1 and Q2. Alright? And U1 is also a linear combination of Q1 and Q2. So that the W defined to be the span of U1, U2 is the span of Q1, Q2. And Q1, Q2 is an orthonormal set, orthonormal basis for W2. Okay. Right, so we construct. So U1, U2 span W2, and Q1, Q2 becomes to an orthonormal basis for W2. Right? And then now we can proceed, right? To continue. Alright? So we can continue up to that WK defined to be the span of U1, U2 up to UK, and this is the span of Q1, Q2 up to UK. Oh, minus 1, okay, minus 1. Minus 1, minus 1. Alright, so suppose, and Q1, Q2 up to UK minus 1 is an orthonormal basis for WK minus 1. Right, suppose we up to here. So you can think about this is the k minus 1 is equal to 2, or k minus 1 equal to 1. That's fine, okay? So suppose we up to now, we construct an orthonormal basis for WK minus 1. Okay, then Then at the k step, we construct UK, defined to be UK minus projection of UK onto WK minus 1, and then normalize it. Okay, normalize it. And what is that? This is UK minus the projection, and the WK has an orthogonal basis. WK minus 1 has this orthogonal, so this is equal to UK Q1 minus UK Q2 minus minus UK minus 1 here, and take the norm. Okay, so you can do it. This is the case state. And then UK is equal to QK plus projection of WK minus 1 of UK. Right? So that is in the span of U1, UK minus 1, and then UK. So that K defined to be span of U1, U2, up to UK minus 1, UK, becomes to the span of Q1, UK minus 1, and QK. And Q1, UK minus 1, QK is an orthonormal basis for WK. This is induction, okay? So from WK minus 1, we construct QK and alright, and so you go on. Because we have m vectors in the linear independent set, so up to m, the m, so we have Qm, W, m minus 1, um minus projection WM minus 1 UM. And this is equal to UM minus UM Q1 here minus minus UM minus 1 minus 1. And here is UM minus Q1 minus UM minus 1 minus 1 here. And the W just equal to the WM, which is the span of U1, U2 up to UM. And this is the span of U1, U2 up to UM. And U1, U2 up to UM is, and also normal say, normal basis for W. And we have that. This is the Graham-Schmidt's procedure. Alright, so this is a procedure for us to construct and also normal basis, okay, for a subspace spanned by a linearly independent set. Okay. So from a linear independent set, we can go forward to find an also normal set. Okay, so this is the standard way to do it. Okay. But that is painful to normalize it, okay? Because every time when we normalize it, we have to do a lot of normalization. All right. So next week I will modify the Graham-Schmidt's procedure a little bit, so that we don't need to normalize it every time, because the normalization takes time. Okay. I recommend you to write a code. If you know you can use melee, that's fine. Or if you are familiar with C, you use C code to write it. Okay. To see the complexity. Okay. So my conclusion, I write a conclusion here as a summary of today's discussion. 7.1 of the textbook. Every finite dimensional inner product space has and also normal basis. Okay, so that the proof is very easy, because every finite dimensional inner product can have a basis, right? This basis is just a linearly independent set. And then by Graham-Schmidt's procedure, we can obtain and also more basis for the vector space. Okay, so it's just an application. So the proof is that by applying the Graham-Schmidt's procedure to a basis for V, right? So So it's done. Okay, so that so I stop here. Okay. See you next week.